So I am Bill Hoffman, as you mentioned. I'm the CTO and one of the founders of a company called Kitware that just happened to find itself creating a build system for C++ called CMake. I really wish we were in Aspen. These are some pictures from the last time I was in Aspen. Over on the right, I'm about 30 miles into a 100-mile race in Leadville. And over on the left, I'm overlooking the town of Aspen from, I think, the Oot Trail. So I really wish we were there in person. Instead, I'm in my office space in upstate New York, Clifton Park. And one of our conference rooms actually has a mural on the back wall of Tahoe Lake. So one tool to build them all, you know, it's kind of a funny joke. Obviously, if you're a Lord of the Rings follower, you sort of get the reference. Hopefully we're not seen as you know, an evil ring to destroy the world of C++, but actually something to help. In fact, on April Fools, we put a blog about CMake, one tool to build them all, and talked about how we were going to integrate a C++ compiler into CMake and avoid having to use a compiler from CMake, which is obviously not what CMake's intended for. So they always say when you're talking to tell them what you're going to say. So I'm going to start talking about Kitware and how we do open source and really where CMake came from. And then I'll give a high-level tour of what CMake has to offer. And then I really want to dig a little bit deep into C++ modules and what this means for build systems, including CMake. And then I'll talk a little bit about how you can learn CMake. And then I'll talk about packaging in C++. So Kitware, we advance science and technology to empower global innovation and meet the world's challenges. This is not what Kitware does. We don't sell software. We never did, and we never really will. So what is Kitware? It's a collaborative software R&D company that does technical computing. We create algorithms and applications, software process and infrastructure, support and training, and open source leadership. The company's got sort of 5 main parts: our high performance computing and visualization group, medical computing group, computer vision group, and a data and analytics. And in the center of that is our software process group, which is where CMake lives. We work with industry, government, and academia. And our customers and collaborators cover many academic institutions, government labs, and many companies. So how does this work for open source? Really what we've done over the years, I mean, Kitware was started in 1998, is we've created this machine, I like to think of it as, that, you know, we've got our contracts and finance team, and we can take commercial and government grants, government labs, and we can prime contracts, we can have subcontractors. So we can basically have these Kitware experts, our customer collaborators, and community users and community developers all work together to develop open source platforms, such as VTK, CMake, and ParaView. Some of the open source platforms we're known for, the visualization toolkit, that really was what started the company, and ParaView, an interactive visualization and analysis tool for scientific data. The Insight toolkit and 3D slicer for medical image analysis. CMake, which I'll obviously be talking more about, a cross-platform build system with abilities for doing testing, packaging, and building software. Our Resonant Informatics and InfoViz tools, the Quiver platform for doing computer vision and video analysis. And we also have open source tools in simulation, ultrasound, physiology, information security, material science, and you get the idea. What do we do for CMake? I mean, you know, how do we make a little money off CMake? Obviously, CMake is well, maybe not obviously, sort of interesting. Some people don't know Kitware does CMake at all, and they're surprised to hear it when they're our customers. And some people think of Kitware as only doing CMake. So what do we do around CMake? Well, we offer courses around CMake. We work with our customers to add new features to CMake. We develop and audit existing build systems for customers, and we sell printed documentation. Along the way, we've had some unlikely but way cool contributors. A recent customer we've had is the Microsoft Minecraft team, and they've worked with us to create some really neat features, one of them being the CMake presets files, which I'll talk a little bit about later. I think one of the most cool things was to see Visual Studio adopt CMake and add support for it. When I hope they don't get mad at me about this, but I'm pretty sure way back in the early 2000s, Microsoft might have sued me for reverse engineering their project files to create the initial versions of CMake. But now they're strong collaborators, and they have worked with Kitware to expand CMake to do better integration with IDEs and provide CMake as part of their Visual Studio C++ project. Another recent customer, which I really wanted to bring up because I can see they're one of the big sponsors for C++ Now, is Bloomberg Engineering, and we've been working with them relatively a little bit of time. But in that time, we've improved the XCOF support in CMake and improved CMake's file-based API to include more information about installed components. Both of these enhancements are available in CMake 20. What's going on here with CMake? We do regular releases, probably about every quarter. It's a regular cadence. And that way our customers are able to see their enhancements in a release relatively soon. So where did CMake come from? Well, it's kind of a neat story. CMake was the lead engineer on a team to create the Insight Segmentation and Registration Toolkit, or ITK. This was a project by the National Library of Medicine. And earlier, I believe around 1993, they created an open source data set called the Visible Human Project, where they had scanned in CT and MR the bodies of a man and a woman that were donated to science. And then after they died, they froze them solid and sliced them as thin as they could and took pictures. And this gave an excellent data set for researchers and engineers in medical imaging. Because now let's say you're trying to register the heart in a CT scan to the heart in an MR scan. How do you know you got it right? Usually it's really hard because you can't cut the patient open and see if you got it right. In this case, the patient was already cut open and you've got excellent reference data. But just having this data out there wasn't enough really to advance science and technology in this area. And what the NLM decided was they needed a toolkit. So they created a C++ toolkit. And as part of that project, Kitware was tasked with making sure it built on Windows, Unix, and Mac. The state of the art at the time was probably a autocomp file on your Unix platforms, a Visual Studio project file that was checked into version control, and then maybe if you're lucky, you had someone on your team that knew how to do something on the Mac. So we set out early to fix that problem with CMake, to create this tool that would allow C++ to be built easily across these platforms. And I have to sort of throw this slide in. It's one I've used before, but it kind of brings back fond memories of Aspen and what was then called BoostCon. I went to the conference and saw David Abrahams gave a talk, and he showed a slide I remember that had C++, it showed Java and it showed, hundreds of built-in cool functionality, and it showed, Python and all the cool things that came with that, and C# and all the things that came with that. And then for C++, we had IO streams. And he said, Boost aims to fix that problem, to give C++ a useful set of libraries and a testing ground and an open source platform to test those libraries before they went into the standard. And I think that's been a rousing success. CMake aims to give C++ compile time portability. You can't compile it once and run it anywhere, everywhere, like Java or Python or C#, but at least we can have the same build tool and files that work across platforms and make it easy to mix both small and large libraries. You remember the original goal was this ITK project, which was meant to be used by researchers. The state of the art back then, you might have a professor read some paper, hands it to a grad student, and says, this looks real interesting. Can you go implement it and see if it works on our data? Grad student disappears for 2 or 3 months, comes back and says, no, it didn't work. Well, what happened? Did the grad student get the coding wrong? Was the paper wrong? What happened? It's really hard to tell unless you actually have the code and the C++ code behind that. And CMake allowed, and plus ITK allowed the researcher to build against this relatively large C++ project and build their own small projects and link them together and create working tools. The basic rules of CMake going into it only depend on a C++ compiler. And this is how we ended up inventing our own language, which I know we didn't do a wonderful job, but CMake also has evolved over time and has continued to update and be able to change. But still, we like to keep this rule, we're not depending on other interpreted languages. Probably back then, it would have been TickleTK, which would have been a disaster, I think, for CMake. And the other rule was to let developers use the IDEs and tools they're most familiar with. If you've got a developer that likes using Visual Studio, if you build a build tool that forces them to use the command line instead of their favorite IDE, they're not going to be as productive. CMake allows you to use these various tools that are out there and the rich C++ ecosystem that's out there with various vendors creating IDEs and compilers and different operating systems and different architectures, but you can still express your build in one tool. I'd like to quickly drop into this. Recently, unfortunately, I don't get to do as much coding anymore with my current position at Kitware, but I grabbed ITK, which has become a rather large C++, very heavily templated library, and it's got wrapping into Python. And I basically did git clone of ITK master, cd into the directory, make a build directory, run CMake with turning on wrap Python, and then I ran Ninja. And what was really cool is I didn't install CMake because CMake came with Visual Studio 2019. I didn't even install Ninja because Visual Studio had that as well. And then along the way, during the build, CMake downloaded cast.xml, pygccxml, swig, and did this very complicated dance of building wrapper code and then having that wrapper code generate code that then generated more code that then was compiled and finally got the complete ITKWrapping in Python with absolutely no errors. So I'll call that a success. It probably took us 20 years to get to where you can do something like that. But the point is you can do something like that today very easily. But obviously CMake isn't all kitware. It's an open source. It's a BSD license. We've had nearly 1,000 contributors. If you look at GitHub, if you Google for modern CMake, you can see there's a lot of really good talks out there. We've had Craig Scott create an excellent book on CMake. And I really like to thank the community. I get sort of the credit for starting CMake. But I suppose one huge shout out to that first icon on the left, that's Brad King, who really does a great job and is really the key architect of CMake these days. Recently, we saw someone create a ray tracer completely in the CMake language. And given our background in high performance computing and the work we've done with NVIDIA, I'm thinking it's probably time to add an NVIDIA object ray tracing engine to the CMake language. Just kidding, obviously. It was pretty cool that someone did a ray tracer in the CMake language, but obviously that doesn't belong in CMake. But Kitware and NVIDIA have collaborated a lot. over the years and added improvements such as fine CUDA and allowing CUDA to be a first cast language in CMake, in that it's treated just like C++ or Fortran or C. And they've worked with us on PairView and VTK support for NVIDIA optics. And coming soon, we're going to work with them for their HPC SDK. CMake and CUDA. So this is a small little project where we enable, call it a C++ project. We have CUDA, and then we can say enable language CUDA. And we can set a few features that we want CUDA standard 14, C++ standard 14. And then I can add a library with C++ file. If CUDA is on, I can add some private sources to it that I'm adding a CUDA file. I can link that library to those GTC compiler flags. And then I can set some include directories, both in the interface and the private. And then we can create an executable that links to this library. And then you can see when it goes to compile, it gets the -i flags right, the standard C++ flags right. It runs the CUDA compiler and VCC, and it links it all together and does all this for you, which is really what the goal of CMake was, to make complicated things easy so you don't have to have an expert figure out how to do all of these things, and to encode it into the C++ and CMake language of CMake. CMake, as you've mentioned, has gotten really popular. JetBrains IDE integrated CMake. And before they integrated CMake, they started doing some surveys and found that CMake is their the most popular tool for C++ at about 53% now, with Visual Studio behind it, but now Visual Studio ships with CMake. An interesting thing I've noticed, if you look at job openings on Indeed and LinkedIn, there's usually around 500 in each of those that mention CMake as a skill that people are looking for in their projects. CMake, the Qt company, has decided to deprecate their QBS build system, and will focus on CMake and QMake. CMake gets lots of downloads per day. So why is CMake so popular? I think it does a lot with a little. Just look at these 3 commands here: add library, add executable, add test. I mean, add library sounds about the simplest thing you would do in C++. And I realize for most people, build systems are boring, horrible things they don't want to talk about. Hopefully I can make it a little entertaining here. But behind this add library is the ability to create shared libraries on Windows, Mac, XCOF systems, AIX systems, very obscure systems, anything from your cell phone to a supercomputer. There's a lot packed behind that small little command. Add executable. We've got to create our final executable that we want to run. And then these can work across many platforms. Add test. We've got a whole testing thing. So a lot happens with these simple commands. Shared libraries, static libraries, many compilers, IDEs, lots of interesting things. I think this is really the reason CMake has gained popularity. The basic CMake workflow: you run CMake on a source directory. Then you can run CMake -build, telling you how many jobs you want. And if I touch a CMake list file, the next time I do a build, it's going to rerun CMake. I can run ctest. It'll run all the tests. And you get the idea. Running CMake, there's a CMake GUI built with Qt. There is a CCMake built with the curses, giving us a terminal command line interface. And then there's CMake for a non-interactive command line. So there's sort of 3 basic ways to run CMake. Running it, the first thing CMake does is read a CMake cache.txt file. This stores all the information CMake has found in its system introspection, and avoids one thing. I remember, I'm an old guy here. You see all the gray hairs. Back, when I worked at GE Research and Development back in the 90s, and a lot of build systems built on AutoConf had a whole bunch of environment variables. And the idea was you'd source all these environment variables that would sort of point to where things are on your system. Then you type make and it would go off and do things. And if those environment variables weren't correct and you type make, things went crazy and the make files wrote stuff all over your disk and it was just a big mess. So the idea is we have this CMake cache, which instead of environment variables, it can be primed with environment variables. But once that environment is set by CMake, it stays. The user can edit that cache, but it stays with that build tree. The user tells CMake to configure, it reads the CMake files, and it gets an iterative process. If you're ready to generate, it can finally generate the native build system. CMake quickly adapts to new technologies as new IDEs come out, Visual Studio releases, Xcode releases. Ninja, I think, was a huge success story for the way CMake can adapt. So this was a command line tool that Google created to build Chrome faster. And I think within a couple weeks, maybe at least a month after it was released as open source by Google, people had ported CMake to it and built a backend for it. And we had it working on all the platforms. There's a question here I'm going to drop into a little bit. Do you think there's still any benefit of using a custom language that people have to learn instead of example Python that's everywhere nowadays? I think there is a little bit. For one thing, I don't want to add that dependency on Python to CMake. I still like the fact that it depends on C++. I think there's a huge community out there of CMake language that's already out there. And probably one of the tenets I left off of that slide was backwards compatibility. We're all about that. We don't want to break someone's build. And another weird thing we saw when KDE adopted CMake, they initially tried scans, and then that actually failed for them. After like months of work, they weren't able to build their core libraries with scans. CMake jumped in and we were able to get things working in a month or so. And I think one of the things that happened is, since that was built on Python, a lot of the projects, what they tended to do was almost like keep their code. So like as C++ grows, everybody grows off of it. The language is a domain-specific language that's there to express the build, and the hard stuff happens in C++, which means to get new features into CMake, they have to go into CMake itself so that the whole community can share them. Modern CMake is built around this idea of usage requirements, where you have target-centric. The target is almost like an object in C++. So I can say target include directories example, and then every target should be fully described how to properly use it. And there should be no difference between external and internal targets. In modern CMake, the directory structure and where your executables and libraries happen to be in that don't really matter. What matters is the diagram that executable depends on library A and library B, and library B depends on library A. And describing that diagram is really what has to happen inside the CMake language. The usage requirements, you can have private ones, and these are only used when the target's being built. The interface ones only consuming targets use it for private interface. The build interface, this is used by consumers of the project inside the build directory, basically. Or you can have install interface, which is used by consumers after the target has been built and installed. So let's look at a quick example here. We have something called trunk, a library called trunk, and we're going to say, we're going to link it, target link libraries it to publicly to root, and then leaf is going to publicly link to trunk. And then you can see when we go to compile our leaf library that it is linking to trunk and root. And below us, if we say that root is private, you can see that when it builds leaf, it no longer links to root. The target link libraries can propagate dependencies for target include directories, compile definitions, compile options, target sources, and link options. Some other interesting features. I mean, there's so many features in CMake, it's really hard to mention them all. But we've recently added Unity or jumbo builds. You can control that with the CMake Unity batch build size. Presets. This was something that came to us through our collaboration with the Minecraft team. And this allows sort of common configuration flags, variables, build directories, generators for a project to be stored in a JSON file for reuse. So there's a CMake presets.json. This would be a version controlled file for sharing between users. And then a CMake user preset.json, which isn't version controlled for local user specific or machine specific setups. So a simple example here is, I've got Ninja debug, and it sets my binary directory relative to my source tree as build debug, and sets a cache CMake build type to debug. And then when I go into the GUI, I can select this preset. CMake also supports precompiled headers now. Excuse me while I silence my phone. CMake also supports precompiled headers. And this is also one of the things about CMake that, over the years, people have been able to do precompiled headers, but it wasn't natively supported until somewhat recently. And this allows speed up of compilation by creating partially processed header files used when compiling instead of repeatedly parsing the header files. In CMake, you would add a library and then set target precompiled headers for that library, creating an interface library of leaf.h, and then listing those private headers that get included in that precompiled header. We've also added support. This came from our work with the Qt company, the multi-config ninja generator, where you can specify, CMake language compiler launchers. And in this multi-config generator, you can build both debug and release off of one build tree, much like you would with Xcode or Visual Studio, but now you can do it with Ninja. The CMake has color now. That was a recent addition, which makes it look a little bit nicer. A cool thing in progress, right now we're integrating file get runtime dependencies with install targets to make the installation process easier. CMake also includes a full cross-platform install system where you can specify rules to run at install time. It can install targets, files, or directories, and it provides default installation locations. So I've got this add library and then install. And again, in these couple little commands, there's a lot going on. And there's a lot of code behind this and a lot of work and effort to make this, as follow standards on different operating systems, and then to work as well as it can across all the platforms. Packaging in CMake. I like to think of this as somewhat of a dark art, simplified by one CMake command. I can remember in the early days of CMake, for our Windows release, we had a Windows installer, and there was one guy at Kitware that knew how to run the installer to create the Windows installer. And there was one machine at Kitware that had it set up to create the installer. So if he wasn't in or something happened to that machine, we weren't going to be able to create a CMake installer. But now we've built that into CMake with the CPAC, which is bundled with CMake, which creates professional platform-specific installers, drag and drop for Mac, MSI installers for Windows. It supports tar.gz files, self-extracting tar.gz files, Wix, Nullsoft, drag and drop, package manager, Debian package, RPM package manager. Essentially, putting almost an expert system behind CMake, allowing users to create these packages and to get their software out there to more people. Using CPAC on Windows, the install command or a zip program has to be installed, Nullsys or Wix. Set up your project to work with CPAC is really easy. Basically, you get the make install to work, make sure your executables can work with relative paths, can work from any directory, then set up some few CPAC options and include CPAC, and then CMake will do everything for you. Testing within CMake. Testing is an integral part of any build system, I would say, or system. Testing needs to be enabled by including ctest or calling enable testing. Once it's enabled, you can say add test, give the test name, and run some command. The executable should return 0 for a test that passes. So a very simple testing system. Ctest, an executable distributed CMake that's able to run these tests. Running it, just go into your build directory, type ctest, it'll run the tests. You can specify -J to run tests in parallel, -R to be able to choose a test based on a regular expression, more verbose mode. You can tell it to rerun failed test to repeat just the failed test. ctest -- help will give you more information on that. We've integrated Google Test, so you can include Google Test, add an executable, target link libraries to gtest, and then gtest discover test was added in CMake 3.10, which queries this text executable and allows it to find new tests without rerunning CMake, just based on what the executables is compiled. ctest allows multi-core tests, and you can set the processor affinity. So let's say you had an MPI test, you know it's going to use 4 processors, and then you do CMake -J 20. You want to make sure that one process gets the right allotment of processors so you don't saturate your processors during the testing process. We've also built a web tool, a LAMP stack-based tool called C-. I like to think that Kitware has been doing sort of continuous integration since before we were even Kitware. It goes way back to our days at GE, where we created this dashboard, which is based on the Six Sigma philosophy and measuring things. So you can go there and see the number of tests passed and failed. You can click in and drill down into things like dynamic analysis and work with things like address sanitizer or Valgrind. CMake has been able to use inside Kitware to improve turnaround with SC cache. At Kitware, we host an internal GitLab. We run a Redis server, which is actually a Linux machine with lots of memory. We run SC cache, and we integrate that with CMake with our CMake language compiler launcher. And we're able to build a really excellent system to speed up our continuous integration and create this sort of whole software process where you have the developers, they develop their code, it goes into some version control system, and then automated testing is happening and triggered, and then the results are specified in some dashboard that the users are able to see. And this cycle of life for software is key for, I think, and one of the reasons that CMake has been around so long as well is that it is very highly tested on all new platforms, and sometimes frustrating for new users. They might come in and do a new feature. I remember when Ninja was being introduced, the person that contributed it only had it working on Linux, and we sort of stuck our feet in the sand and said, hey, until we get this working on Windows and Mac, we really don't want to make it part of CMake. We want to get it out there so that it's true cross-platform. Okay, that's sort of my whistle-stop tour of CMake and its features. And there's obviously a lot more features inside CMake. I encourage you to look into it or ask me questions. But now I'd like to talk about C++ 20 modules. CMake and the future of C++. So let's look at this small example here. We've got a main that says import hello world, a hello world.cpp, which says export module hello world. Okay, down below, cc -o main.cc cpp and cc hello world is suddenly an error in C++ because hello world now has to be compiled before main is compiled to make sure that export happens. But wait, CMake has for 16 years experience with modules. And how do we have that? because Fortran actually has modules. And I can remember pitching that to Fortran developers, because what Fortran developers had to live with modules before we added this support was basically typing make over and over again, because each time it got a little bit further and more modules got compiled until it actually converged on a build. So what needs to happen, and I'll describe the process more, but the point is, to do this, we needed to add a Fortran parser into CMake, and you can see that was done in 2005. In 2015, we added support to the Ninja build tool to handle dynamic dependencies of Fortran. And this was funded by the Trillanos project, which is a high-performance computing project out of Sandia National Labs. And we actually had to fork the Ninja project, and that fork lasted for many years. And we've tried to work with Ninja, but it was a rather intensive change for Fortran, which they were somewhat interested in, but not completely. But in 2019, Ninja merged all of our changes to support Fortran because of C++ 20 modules, realizing that to support C++, Ninja was going to need this work. So how do Fortran modules work? Well, if you look at module math, when I compile this, it creates not only math.o, but math.mod. And then I've got my program main, which uses math with this little use math, and main.o needs math.mod. So the input to CMake is actually, target-based. I've got library A, library B, library C, and each one of those has, say, 3 Fortran files. And this is what CMake gets as input. So let's look at the build graph for a single source. So our A1.F90 goes through a preprocess step. So essentially running like the equivalent of CPP over the Fortran file, and that creates a preprocessed version of the Fortran 90 file. Then we scan it, which is where our Fortran compiler comes in, which creates the provides and requires, we call it. What does this object provide as far as modules, and what modules does it require? And then at the end, we collate all the provides and requires for a target to create the compile order. And now we can compile the object files, because the build system needs to know what order to build the object files. And in order to do that, it has to at least preliminarily parse those files to find out what their provides and requires are. So a single target looks something like this. Each of the sources of that target gets preprocessed, and then each of those preprocessed files gets scanned into provides and requires, and then they get collated into a target level dependency file, which tells us which order to build those object files. So if we look at a single target, you can see here that A.1 produces math.mod, and then that goes into the compile step for A.2. So now everything, we know which order to build them in order to math.mod, and we know that if A.1 is changed, then A2 may need to recompile, but A.3 will never need that. So you can see it gets somewhat complicated, but again, it depends on being able to understand who provides what and who requires what. The build graph for multiple targets, basically the dynamic dependency file for each one of them. We build each one, and then we make sure those targets exist in the right order for it all to happen correctly. So how does CMake do this? We have a Fortran parser, as I mentioned a few times, based off a program called MakeDep F90. Patches were made to Ninja to allow, they were upstream, and the dynamic dependency collator that's inside CMake. So now for C++. C++ now, right? What happens here? So if you look at this graph, the the numbers show sort of the order of things that happen. So at the 0th level, we're given a bunch of C++ sources. We have to scan and collate those, and that's sort of our 2nd level. And then once we've got our 2nd level, since we know this order, we know that A1 is an order 3. It can be compiled right away. And we know it produces math.mod, which means that A.2 can't happen until A.1 is compiled. So it's on this 4th level. But A.3 can happen in parallel with A.1, and it's a 3rd level. So with the C++ compiler's help, this build graph will be able to skip the separate preprocess rule within the build and instead use a single scan rule. Let's look at a more complicated example. Let's look at compiled code generators. So imagine you have some code that you compile in the middle of your C++ project, and then that code is used to create an executable, and that executable is used to generate some code, which then needs to be compiled. And let's throw that into the mix. So at our 0th level, we have A1.cpp, and A2.cpp needs to be scanned and collated. But you can see A3.cpp is at the 5th level. And then at the 8th level, we got A.1 that creates math.mod. And you can see this generation process. And eventually, it can go to build this generator and go into compile and eventually build, lib.a. So build graphs can get very complicated very quickly without that much going on. So what are some options? Option 1, we could scan the sources independently and then collate. We could scan the sources all at once and then collate. Each of these has different trade-offs. Option 3, scan sources and collate all together. This would require a lot more work from the compilers, I think. There's a great reference paper on this found on that. I'll give you the links here. My slides will be up so you can click through this. And there's a proposed format for becoming a standard for C++ compilers. The bottom line is build systems need to throw the build system. The compilers need to throw the build systems a bone for C++ modules. Please don't make CMake have to include a C++ parser. That, I think, would be the worst thing in the world for CMake and other build systems. But I think we're really on a good path to get this into compilers. So moving on from C++ modules, what's the best way to learn CMake? I'm often asked this. For one, don't copy someone's CMake code from 2010. CMake is an evolving tool, and it has changed a lot over the years and has improved over time. I would encourage people to Google for talks on modern CMake, watch those talks, understand how CMake works. Professional CMake by Craig Scott is really good. We have a very active discourse forum, discourse.cmake.org. The online documentation can be found at cmake.org. There's a tutorial that's part of a guide, which I'll talk about. The CMake guides, we have CMake tutorial, CMake interaction guide, using CMake dependencies guide, importing and exporting guide, and IDE integration guide. So our documentation, this is one of the things that we're working on and has improved. And the code with the tutorials, one of the problems is that they get out of date. So I think it's critically important that that code is tested as CMake is built. So the tutorials are now part of the CMake build system and testing system. But we've used markup to specify a literal include, which points back to the source code, and you're able to have nice documentation that references code that's actually being tested. Our Mastering CMake book has grown a little bit old, and what we're doing to help that is we've now made it open source. This was just done last week, and I'm announcing it now at CppNow. But it's on our GitLab site, and we'll be generating those documentations. Right now, we've basically ripped out all of, or most of the stuff that's incorrect or showing old ways of doing things, merged in our guides, and eventually we'll work to clean this up and have an online version of the book, plus we'll still provide printed copies if someone wanted to purchase those. Putting it all together. So most software is not an island and depends on other libraries and other software. So one way to do this is through CMake's find modules. CMake has a really rich set of find modules. There's over 150 find modules provided by CMake. And in modern CMake, those modules use imported targets, which make it look no different than as it was built by the project. So if we look at this example here, we do find PNG required, meaning that CMake will kick out an error early on, basically at the configure time of CMake, if PNG isn't found. When it is found, then we do an add library trunk shared that links trunks, that builds this trunk C++. And then we do target link libraries trunk private to PNG::PNG. And you can see we're linking to a target there and not using -L flags or listing the path to the PNG library. We've imported that target as if it were built within CMake. Exporting targets, CMake has this idea of an exported target, and install rules can generate imported targets for other builds, other versions of CMake. Oh, I'm going to pause here for a second. There was a question about the C++ modules. I'm going to back up here a little bit. Jumped ahead. So back here, the first question is, when do you expect C++ 20 module support to be released with CMake? It actually is in CMake Master now, the functionality for it. There are no compilers that concurrently do what we need, but there is, Ben Bakel at Kitware created a Docker image that has C++ 20 modules implemented in GCC that does what we need for the provides. But inside CMake code right now, there exists, and it's marked as experimental. But again, we're kind of waiting on the compilers. The next question is, can C++ 20 modules work with all generators? Right now, they would work with the Ninja generator, and we will get the makefile generator soon. We're a little bit waiting on the compilers to implement what they need. And then I assume Visual Studio will be able to handle them themselves. So since we're just generating Visual Studio projects, those Visual Studio projects would be able to hand it through what Visual Studio does. So I think, does that answer the questions? Are there any further questions about C++ 20 modules out there? I'm not seeing any, so I'm going to move on. Again, so back to exporting targets. So I create a simple library called Parasite with a single source called eatleaf.cxx. And then I install the target Parasite, root, trunk, and leaf. and I export tree targets. I install export tree targets, destination lib CMake tree, and this installs library and target import rules. So in our prefix of our install, there's going to be a lib/parasite.a. Under that prefix, there will also be a lib CMake tree/tree targets.cmake, which another find package call could find that tree targets and pull that into another project. Again, acting as if this target was built as part of this tool. Conan, the package manager, has some a thing called CMake deps, and I believe there's a talk coming further on in CppNow where this will be covered in more depth. But the idea is to help people create these config.cmake files. You can also do it through the CMake language. And we've had sort of success of other projects like Qt, when it had the CMake build system, also provided CMake target.cmake files as part of its build system. Even though the build system wasn't CMake, they were able to create those CMake files and make it easier for people to use their project with CMake. Boost did the same thing as well. CMake also has external projects. This is a system inside CMake for referencing a project. And this happens at build time. So I say external project add foo. I give it a Git repository, a tag that I want. And I've got a couple projects here, foo and bar. And bar depends on foo. And what CMake does with this is at build time, not configure time, when I type Ninja or Make or run Visual Studio, it's going to clone the project, foo and bar, and then run the build system on them, and then build them. An interesting thing that happens here that isn't quite ideal and confuses people at first is since this is delayed to build time, any targets that come out of this can't be found because they won't exist at configure time of the main project. The way around this is to add your own project as an external add project. So we call these super builds in CMake, where you have your project plus all of its dependencies, and each one of them is an external project add. And the reason this is pushed off to build time is because obviously these can be lengthy things. If you were to type, CMake configure, you want to keep that relatively fast and to show those errors right up front. So if there's errors in the configuration, you don't want to go through, all of building foo and find out that there was an error in the basic configuration of your project or some missing dependency. So this has to be pushed off to build time. Another thing that does at configure time is fetch content. And this is more useful for pulling in source code into your tree, or possibly precompiled binaries that you can check and pull down content at configure time so that it actually can be available during the global build and you don't have to turn your whole project into it. There are pros and cons of both of these approaches, but they do allow you to create sort of mono repositories and self-contained builds for a project. So this gets to package managers. Obviously, I've been talking about CMake, one tool to build them all. And I think, CMake's external project and fetch content, they can only go so far. CMake is a great build tool, and I'd obviously like to see more projects using CMake. I think it would make the package manager's job much easier if, all projects use CMake. It would make a lot of people's lives easier, I think. But there are complex software systems They require many packages in lots of different languages, interactions, and these are probably best handled with a package manager. Conan, VC package, SPAC are all good options for managing large C++ projects. Let's take a look. We've been working with the SPAC team a little bit at Kitware, and this is one of their slides showing that HPC simulations, high performance computing simulations, require, essentially, they have these icebergs of dependencies. This one, MFEM, high order finite element system, requires 31 packages and 68 dependency edges. This one down here, the MU-MMI, cancer drug interaction, integrates MD, HPC scheme, has 98 packages, 248 dependency edges. And these very complicated systems probably wouldn't scale to a single CMake system. And even if you could get it to work, you'd run into problems of probably doing snapshots of different systems and pulling them together into the build. Whereas a package manager allows more independent upgrades of different packages along the way and more up-to-date packages, and handling these massive amounts of dependencies. So here's an example that the SPAC team showed me. Helped streamline development for LANL C++ code team using PyTorch. Before SPAC, integrating PyTorch with the C++ code for the PowerPC 64LE and MPI was very painful. Everyone built their own Python and PyTorch from scratch because it was this unique architecture. People wrote scripts and passed them around. Scripts slowly accumulated modifications and magic. Days were spent trying to build and debug the differences. With a package manager SPAC in place, versioned reproducible SPAC environments through a SPAC.yaml, SPAC.log files were created. Standard environments were created in a shared team directory. Any team member can get a customizable working environment in less than 20 minutes. You can change the Python version, change PyTorch versions, etc. Reuse prior builds using SPAC build caches. Recently, Kitware has been working with Lawrence Livermore Laboratories to add Windows support for SPAC. So basically the future. What would I like to see for C++ and CMake? Number one thing, if all I want for Christmas is C++ compilers to provide a build system interface to collect C++ 20 module dependency information. We've got a great start with that. We're working on the interchange file format, but I'd really like to see that move forward. Also a cross-platform standard for the information found in the CMake config files. Right now they're in the CMake language. Certainly wouldn't be opposed to making them some other language, some sort of unification between PKG config that works cross-platform, but provides all the information the build tool really needs, would be awesome as well. I'd really like to thank the CppNow committee for entrusting me with this keynote speech. There's still some time left over now for questions. And obviously, I'll take email questions, bill.hoffman@kitware.com. If you want to learn CMake or write CMake build system, go to the guide or manual on exploring CMake documentation. Explore the CMake documentation. And again, I'd really like to thank everyone for coming to this presentation. And hopefully I can get some good questions and interact with folks now. Okay, we've got a question here. Is CMake external project add the best way to integrate with Conan? I actually can't answer that question, but I know that there's a speaker at the conference that is going to be talking about Conan later on, and it's probably best to ask him. Next question is, when should I stop using fetch content and start using a package manager? It really depends on your use case. You know, if you've got a a small ecosystem, you know, that, you know, like CMake itself, to build CMake, I'm probably not going to use a package manager to build it, because I want CMake to be able to be self-contained, and again, depend on just the C++ compiler. And it depends on your needs and exactly what you're trying to do, as opposed to you know, how big your system is and how it integrates, and what platforms you're targeting. I know with like the Minecraft system, they're not using a package manager, and they've got it all contained within a single build system. So it really depends on what you're doing. Next question, what is the easiest way to extract CMake target properties? Inner target dependencies, transitive compilation flag to be reused by package managers, i.e. CMake deps to automatically generate config files. You can use the CMake built-in properties to do that if you've got a CMake project. I think that's probably the most CMake way to do it, and probably the way I would recommend doing it. Let's see. Next question. Any recommendations you have for large C++ code base with wrappers being generated from a large variety of target landscapes via Swig, CPython, and ... So I'm not sure what they mean by recommendations for large C++ code base with wrappers. Certainly, we've done that at Kitware. ITK does it. VTK has wrappers. We're also working on a project called AutoPyBind11, which uses PyGCC-XML and CastXML to automatically generate PyBind11 projects. But yes, for Swig, a good example would be to look at the ITK project. You could talk to them on the Discourse project to see how they're doing it. But basically, that can be done, built out with CMake's custom commands, which are part of the CMake process and build system, and certainly fully capable of handling very complicated large projects with different target systems using Swig and other generators. Let's see, answer that live. I think I might have just closed a question by mistake. If I did, feel free to re-ask it. Next question. You mentioned CTest can run Google Test. Can CTest work with other testing frameworks like Boost Test? Yes, I believe Boost Test is one of them that we can do. And there are several others. And we could easily add more if you're interested in those. The fact that we've got it working with Google Test shows that it's easily integrated. At a minimal level, it's certainly very easy if you just take your the test command and then turn them into add test calls in CMake. If you want CMake to do something like it does with gtest on a system we don't have, you would have to do a little more work, but it probably wouldn't be that much work. Next question. Does CPAC also integrate well with Conan packages and configurations? Again, I don't have a lot of experience with Conan myself. I would assume, CPAC integrates well with CMake, So if you've got a project that's got install rules that work and are able to generate a CPAC rule that it should work inside any package manager. Okay. Let's see, back to the, you mentioned C++ running Google tests, can C-test work with others? Basically, any exe that returns 0 versus non-zero can work. And that's basically, yes, that is a good answer. You can also do more complicated things if you wanted to look at the regular expressions in the output, if you wanted to look for certain text. And again, something interesting that you might be interested in looking at is C-. We run an open C- server, so you can test it out yourself. You can obviously run it yourself. All right, let's see. There's another question. You mentioned that CMake doesn't put constraints on the code-based directory tree. Still, any recommendations on do's and don'ts for the tree structure? One big don't is don't do in-source builds, although they're supported. I know that's not quite the question, but it triggered me. That's one of my pet peeves. I always hated that with autoconf, the /configure make, and then it spills all of its build files all over your source tree, potentially messing up any version control systems and sort of making a mess of things. So obviously, CMake natively supports, creating a separate build tree and building it, but I understand the as far as designing your source tree, I mean, I think it's lay it out what makes best sense for your developers. The main point of that is that CMake doesn't require a tree structure like it used to, sort of in pre-modern CMake. Really had to sort of walk into things, and your directory structure had to be a hierarchy. It still could be, and that might make perfect sense for your build system, but it certainly doesn't have to be. And I think that's the key point, that you're really thinking of these targets as objects and doing object-oriented build systems. That the CMake is code, and that code is object-oriented, and your targets are the objects, and they're self-contained, and they tell the world, what do you need to do to build me, and what do you need to do to use me, both during the build and install. So as far as your tree structure, it kind of depends on what you need. I wouldn't, necessarily create it, as a top-down hierarchy if you don't need that anymore, if it makes more sense to spread it out. And also, yes, Matthews will be speaking about that a lot on Thursday. You're welcome to join us there at the Conan talk. Let's see. Done with that one. Let's see. Done with that one. Question, are there any plans to support Bazel? No, there are no plans to support Bazel and CMake. I think they're really both sit sort of at the same high level, and generating Bazel from CMake really wouldn't make much sense. We've looked at it in depth, but it just doesn't really make sense to generate a Bazel backend for CMake, given what Bazel wants to do and its monolithic build. So really the answer there would be no. Next question. Are there plans to set up easier use of libraries that insist on using other meta-build systems? GN is, for me, personally, an annoying example. I'm not sure I understand the question. Maybe someone out there in the chat could update that, and I'll skip it for now and move to the next question. The next question is, will there be a Visual Studio Solution VC Proj to CMake converter that preserves VC Proj configuration structure? Currently unavailable. Converters simply expand everything. The simple answer to that would be not that I'm aware of, and that would probably be a lot of work and would probably be something the Visual Studio team would be most capable of handling. I know on the back end, when they pull in a CMake project, they use Ninja as their build system directly, which is sort of interesting. But yeah, I'm not aware of anything like that, and that would probably be a really good question for the Visual Studio team. Unless anyone has any further clarifications on their plans to set up an easier use of libraries that insist on other meta build systems. Okay, we're moving over to another question. You were using Ninja as well. Do you recommend that over regular make, and why? Yes, I would recommend Ninja over regular make. The Ninja build does a much better job with parallel, which is essentially what it was designed for. It has a more global view of all the dependencies, as opposed to the way our make files work. Although we've done a lot of work on the make files and probably will do another iteration. But right now, I would say the best generator in CMake is the Ninja generator. And it has the best features for doing parallel, and it's supported on lots of platforms. So I can't see a great reason for using make files unless you've been traditionally using them or depending on them for some reason. And again, yeah, I think they handle parallel a lot better. Ninja does over make, so I would highly recommend them. Okay, here we are. We have a clarification. GN is Google's program for generating Ninja files. Yes, I did know that. So it's kind of competing with CMake. I'm not exactly in a position to make them stop using it for libraries they make. Okay, I see what you're saying. So are there plans to set up easier use of libraries that insist on using other meta build systems? Like the, I suppose the easiest thing in CMake right now would be external project, would be the way to integrate other build systems, or something along the lines of fetch content and custom commands to get those builds together, which is probably a little bit on the clunky side, but that would be where the state of the art is right now. But CMake is a dynamic system with lots of effort going into it. So I could see that growing. But yeah, right now I'd say external project would be the way around that. And thanks for putting the clarification up there. It's for those who don't know, it's very interesting doing a talk like this. I really wish I was in front of a whole live room. Got two computers, one that shows me and lots of silence, and another one showing me the questions as they pop up. So I get to hear a lot of myself. Is there a plan to add support for arbitrary multi-configuration generators? I'd like to compile lots of versions of my projects in parallel. For instance, with and without SIMD instructions. So the closest thing we have to this now, I think you'd want to look into is the Ninja multi-config generator. I think it could probably do what you want today. I mean, right now, you could set up your own separate configuration. We have debug, release, rel with debug info. We have those configurations, but you could create your own. One that has SIMD, you could do the Ninja multi-config, and then run a Ninja process at the top that builds all of them together. So I think you could do that today with the Ninja multi-config generator. As long as we're by the campfire here, I think I just reminded myself the rel with debug info. Some people might wonder why we have such a really weird name for release with debug information. And this goes back to Visual Studio 6, in that when you told Visual Studio 6 to build, when you specified the configuration, it basically did pattern matching. So if you said build debug, and you had a configuration called debug, and one called release debug, it would build release debug and debug. So you had to come up with unique names to build. So rel with deb info is the unique name for release with debug information. A little history, showing off my gray hairs, and that was from Visual Studio 6, probably back in 2001. And I just answered all of the questions. There are no open questions. Any more questions? Anybody else want to jump in with a microphone and let me hear someone besides myself?
Thank you, Bill. That was an excellent talk. This is Kevin, volunteer with the conference. If there are no other questions, we will call it.
Thank you very much, Bill. It's great.
Yeah, thank you very much for giving me the opportunity to talk today, and hope I didn't let you down. I had a lot of fun talking and remembering, all the fun stuff, and I hope I got out, the message of where CMake came from and some of the highlights that are there. I know.
Yeah, that insight into the history is great. It lets us appreciate tools better when we use them to understand where they came from and what they're about. So thank you very much. I hope you're going to be around for this conference. I hope you're going to be in the audience for the Conan talk. That would be great to have you there in case questions come up.
Yeah, that would be fantastic. I'm hoping to.
All right. Enjoy the conference.
All right. Yeah. Thank you very much, John.